I will present the solutions for item number 3 of our homework number 2. Problem statement. Let the components of matrix X correspond on tests in arithmetic speed or x sub 1, arithmetic power or x sub 2, memory for words or x sub 3, memory for meaningful symbols or x sub 4, and memory for meaningless symbols or x sub 5. To observe sample covariance matrix in a sample of 140 is as follows. For item 3A, we need to find the partial correlation between x4 and x5 holding x3 fixed. For item 3B, we need to find the partial correlation between x1 and x2 holding x3, x4, and x5 fixed. For item 3C, we need to find the multiple correlation between x1 and the set x3, x4, and x5. For item 3D, we need to test the hypothesis at the 1% significance level that arithmetic speed is independent of the 3 memory scores. And for item 3E, we are to use Fisher's Z to test the hypothesis of rho sub 23 is equal to 0 against the alternative hypothesis of rho sub 23 not equal to 0 at 5% significance level. To solve for items 3A to 3D, we first let the matrix X as x1, x2, x3, x4, and x5 transposed. We also know that an unbiased estimator of the sample covariance matrix X is given by S is equal to 1 over n minus 1 multiplied by a matrix A. Since we have a sample of 140, we have 1 over 139 times matrix A. Hence, we know that matrix A is equal to 139 multiplied to sample covariance matrix S, and this leads to the following results. Solving for item 3A, we need to turn the original matrix A into a reduced matrix containing only the variables needed for this problem. Hence, we let a permutation matrix L as follows. The permutation matrix L is a 3 by 5 matrix containing 1 on the 4th column of the first row, 5th column of the second row, and 3rd column of the 3rd row, and 0 elsewhere, such that when we premultiply the permutation matrix L to the matrix X, we have x4, x5, and x3 transposed, which follows a normal distribution with mean L times mu and variance L times sample covariance S times L transposed. We also partition the matrix X as X superscript 1 equals x4, x5 transposed, and X superscript 2 equals x3. Then we have the following reduced matrix A equal to permutation L matrix times original A matrix times L transposed. Then we solve for A11.2, which is equal to A11 minus A12 times A22 inverse A21. To get A11, we obtain the following elements from our reduced A matrix, and the resulting matrix is as follows. Meanwhile, to get A12, which is equal to A21 transpose, we get the following elements from our reduced A matrix, and the resulting matrix is as follows. For A22, we get the A33 element of the matrix, hence we have 3202.56. Now obtaining A11 minus A12 times A22 inverse times A21, we have the following result. Therefore, to obtain the partial correlation between x4 and x5 holding x3 fixed, we obtain the ratio of a45.3 with the square root of the product of a44.3 and a55.3. Hence, we have 59.08 divided by the square root of 150.40 times 69.63. This is equal to 0.5773. Now, to solve for item 3B, we don't need to use the permutation matrix since all of the elements of the matrix X are of concern of this problem. We partition the matrix as follows. Let X superscript 1 equal to X1, X2 transposed, and let X superscript 2 equal to X3, X4, X5 transposed. Then we solve for A11.2 with the same process in item 3A. We have the following. And obtaining the difference, we have this matrix. Therefore, to obtain the partial correlation between x1 and x2 holding x3 and x4 constant, we get a12.345 divided by the square root of a11.345 times a22.345. This is equal to 425.30 divided by square root of 796.42 times 1219.98. This is equal to 0.4315. To answer item 3C, we need to define a permutation matrix L to reduce the matrix A in order to contain only the variables needed for this problem. We let L be a 4x5 matrix with the following elements. The elements of L are equal to 1 for the first row and first column, second row and third column, third row and fourth column, and fourth row and fifth column, and 0 elsewhere. Such that, by multiplying L to the matrix X, we have x1, x3, x4, x5 transposed, which follows the normal distribution with mean L mu and variance L times sample covariance matrix X times L prime. We also partition the matrix as X superscript 1 equal to x1 and X superscript 2 equal to x3, x4, and x5 transposed. We then have the following. A11 equals 800.64. Matrix A22 equals the following, and matrix A12 equals the following. To compute for the multiple correlation between x1 and the set x3, x4, and x5, we obtain the square root of a12 times a22 inverse a21 divided by the square root of a11. This is equal to the following, which is then equal to square root of 4.22 divided by the square root of 800.6. The resulting answer is 0.0726. To solve for item 3D, we know that from item 3C that the multiple correlation between x1 and the set x3, x4, and x5 is equal to 0.0726. Using this, we test the null hypothesis that arithmetic speed is independent of the three memory scores, against the alternative hypothesis that there exists a positive relationship between arithmetic speed and the three memory scores. The decision is to reject the null hypothesis at 1% significance level if n minus p divided by p minus 1 times r squared divided by 1 minus r squared is greater than f tabular value with degrees of freedom equal to p minus 1 and n minus p at 1% level of significance. Plugging in the values, we have 140 minus 4 divided by 4 minus 1 times 0.0726 squared divided by 1 minus 0.0726 squared greater than the f tabular value with degrees of freedom 4 minus 1 and 140 minus 4 at 1% level of significance. This leads to an answer of 0.24, which is not greater than the f tabular value equal to 3.9289. Since the test statistic, which is equal to 0.24, is not greater than the critical value of the f distribution, which is equal to 3.9289, we do not reject the null hypothesis that arithmetic speed is independent of the three memory scores. To answer item 3E, we use Fisher's Z to test the null hypothesis that row 2, 3 is equal to 0 versus the alternative hypothesis that row 2, 3 is not equal to 0. First, we compute for the sample correlation coefficient between x2 and x3 as follows. The sample correlation coefficient between x2 and x3, or r sub 23, is equal to a sub 23 divided by square root of a22 times a33. To obtain r23, we consider the original matrix A. Hence, we have A22 equals 1,335.79, A23 equals 307.57, and A33 equals 3,202.56. We then solve for the sample correlation coefficient between x2 and x3 as 307.57 divided by the square root of 1,335.79 times 3,202.56, which is equal to 0.1487. Second, we solve for the Fisher's Z transformation of the sample correlation coefficient between x2 and x3 as follows. 1/2 times the natural log of 1 plus sample correlation coefficient of x2 and x3 divided by 1 minus the sample correlation coefficient of x2 and x3. This is equal to 1/2 the natural log of 1 plus 0.1487 divided by 1 minus 0.1487. Which leads to an answer equal to 0.1498. We also compute for the zeta, which is equal to 1/2 the natural log of 1 plus the hypothesized value of the population correlation divided by 1 minus the hypothesized value of the population correlation. This is equal to 1/2 the natural log of 1, which is equal to 0. We also note that the standard deviation for Z23 is 1 over square root of n minus 3. To compute for the Z statistic, we have Z minus zeta divided by 1 over square root of n minus 3. And this is equal to square root of 140 minus 3 times 0.1498 minus 0, which is then equal to 1.7535. Therefore, the absolute value of Z statistic equal to 1.7535 is less than the critical value of a standard normal distribution at 5% significance level, which is equal to 1.96. Hence, we do not reject the null hypothesis.